how much a vector looks like another vector. This is a very important geometrical question. So let's see how the inner product allows us to gather this information. You find here on the right hand side, well, the typical vector 1, 2, and in green, the vector -2, 3. And let's ask, how much do these two vectors look alike? Well, one way to go about it is to compute the inner product between both. So 1, 2, inner with -2, 3. Well, you just multiply the entries. It gives us 1 times -2 plus 2 times 3. So this is just a number. So you get here a -2, you get here a 6, so you get 4. Very easy. But remember again, remember that another way to compute the inner product, which is the magnitude of the first vector, which in this case is 1 plus 2 squared, square root, plus the magnitude of the second vector, so -2 squared plus 3 squared, times the cosine of the angle between both. In other words, let's just rearrange this formula. So let me just do the calculation first. So it says square root of 5, and then the square root of 4 plus 9, which is 13, cosine theta. So let me just rearrange. From here we conclude that the cosine of theta must be 4 divided square root of 5 square root of 13. Very important result, because through the inner product I can now get a glimpse at what the cosine is. I get a trigonometric equation here. The known is theta, the angle between the two vectors, the angle here. But if I know the angle, that measures how much these two vectors look like each other. Can you see? If the angle is 0, they are coincide. If they are 90 degrees, well, one and the other have nothing to do with each other. If they are more than 90 degrees, the inner product is negative. So essentially, the angle or the sine of the cosine or the magnitude of the cosine tells us how much it evaluates the angle. See? So when comparing two vectors, you can either give me the angle or you can give me the cosine of that angle. Also fine. I can also get an idea if they look like each other or not. So this is important in computing the similarity between two vectors. But more than that, let's see something else. You find on the second picture here, again two vectors, very easy. The vector EV, which is essentially 1 minus 1 divided by the square root of 2, and the vector U here, whose entries are 1 and 3. Let's make the inner product and see what happens. If you dot EV with U, it gives us, well, multiply the constants. 1 times 1 is 1, 3 times minus 1 is minus 3, and you divide by the square root of 2. So you get minus 2 divided by the square root of 2. Very easy calculation to do. But now let's turn to the second definition of inner product, which is the magnitude of this vector, which is in this case 1, times the magnitude of this vector, which is just u, so the magnitude of u, times the cosine between both vectors. Let me draw the angle here, theta here. But now, very important idea. What does it mean, u times cosine theta, from the geometrical point of view? This quantity here is exactly this distance here. So this is u cosine theta. Can you see? Geometrically, this is what it means. U is the length, and cosine gives us that. So in other words, the inner product of a vector with a unit vector gives us the projection of u along the unit vector, in this case this distance. You can almost imagine that we have a candle here on top, shining light below. And what you see here in this distance is a shadow, the shadow that u casts on the floor, and the floor lies along EV. Can you see? Very important idea, this one. Every single time you dot a vector with a unit vector, you are getting projections. Okay? Let's now look at a specific example of this on the third picture, because I have here a vector u, again the typical vector 1, 2, and two unit vectors, ex and ey. Let's compute the inner product between these three vectors. So u with ex is very easy, because ex is just 1, 0. So the calculation is 1 times 1 plus 2 times 0, which is 1. Inner product with ey gives us 1, 2, 0, 1. 1 times 0 is 0, plus 2 times 1, which is 2. So again, by doing this calculation, it picks out this quantity and picks out this quantity here. Can you see? Which is exactly what you find here. The 1 lies along this distance. So this is the 1 here. And the 2 is this distance. Can you see the shadows? The shadow on the floor with the light shining on top is the inner product u with ex. If you now have the projection candle on this side shining light in this direction, so from this, the shadow now is on the wall, and the shadow on the wall has length 2. Well, it's what you find here. So this is very important, because now you can get the components. You see, you can get the components of u along these vectors, and now decompose. You are decomposing the u vector along ex and ey. And therefore, I can write the u vector like this. So u is essentially something, some quantity, times ex plus some quantity along ey. But how much is that quantity? Well, we just have the answer here. Is the shadow along ex. So u inner with ex, the number, and how much I want from ey, well, is the shadow. Why? Can you see the idea? So u is a number times ex plus a number times ey, but the number is computed through the inner product between the vectors. Final warning: this only works provided that our basis that we are using is orthogonal and unitary, so it's S length 1. That's it.